Today, for the science seminar today, I want to review some of the features of Sorcerer, our source localization software, and to talk about some of the research and development we're doing for the next generation for Sorcerer and for a companion application that we'll add for transcranial electrical stimulation planning that we're planning to call Synchronizer. And some of the issues are how to do source localization. What are the important physical parameters of electricity that change and influence how we measure the brain's electricity and how we interpret what we measure? And some of the issues will have to do with how do we validate the inferences we make about source localization. And source localization is the process of measuring the electrical activity at the head surface, but understanding that where that electricity, where the voltage fields that we measure come from is a somewhat complex problem. And although some scientists have somewhat superficially considered this as an insoluble problem, it can be solved with enough constraints, with enough parameters that we can impose with reasonable assumptions about how the electricity is conducted through the head space. So let me start with this, and I want to emphasize that today we'll record this for possible later use and training, but I want to make this informal. I've not really prepared this in a careful way, and I think the natural questions that you'll come up with could be very important. So please interrupt at any time with questions or comments that you may have. So we're the Brain Electrophysiology Laboratory Company. And the Brain Electrophysiology Laboratory started a number of years ago at the University of Oregon, the basement of Straub Hall. And we eventually made a company, Electrical Geodesics, which we sold to Philips in 2017. And at that point, we created Bell as a company. Part of it is so that we could continue our research, but part of it is to allow us to take a fresh start at generating next generation products for measuring and analyzing the electrical activity of the brain. So the Bell System 1 is a complete EEG system and soon to become a transcranial electrical stimulation system. The elements that include the geodesic head web, a new generation of electrode systems. Also, it includes the electronics for high resolution, low noise amplification using modern components, using the latest generation of chips and electronic technology. And then visualization software that we built to be as usable and user-friendly as possible after many years of experience working with people who use EEG both in research and in the clinical setting. So the complete system really depends upon integration. And part of this integration really is training so that everything is potentially usable, and then it does become usable because we integrate it in a careful way. An essential part of this is the laboratory information system that we call FLOW, Forward-Looking Operations Workflow. And the theory is that if we can do computing ahead of time, then when you, as a user, want to make sense of what the computing has done, it's already ready. We've been forward-looking by creating it. So the FLOW provides a general purpose laboratory information system. So we give you an interface to the data in your laboratory as it's organized, and then to operations that you can perform with the data. And among these are visualization, including source localization. And the package that we do this with, we call Sorcerer. And that'll be the main focus of what I'll be going through today. But part of the integration with Sorcerer really has maybe two aspects that I'll emphasize. One, we want flexible open source tools for analyzing the brain signals. So we have interfaces with popular software for open source EEG analysis, including EEG Lab and MATLAB and MNE in Python. And we integrate these within the Jupyter Notebook platform. This is a very user-friendly and yet extremely powerful and flexible framework that each user can then create new packages and new algorithms for data analysis. We can lock these up into a container so they're reproducible and then shareable with other laboratories. The Jupyter Notebook operations can then be packaged back into Flow so that the user can make sense of these into a integrated workflow. A key part of this, though, that's somewhat different from other laboratories, and it's because we started fresh with Bell and kind of redesigned the system from the ground up, is that we assume that source analysis is part of every EEG experiment. Now, of course, we don't force customers to do that, but we try to make it easy so that as you collect the data, you can relate it to the brain and not just to the electrodes where it was recorded. So Sorcerer then becomes an interface to the brain's generation of the measured data. And there are a number of elements that we've integrated with it. The human head has conductivity properties, and those properties determine how the signals translate from their position in the brain, where they're generated by the brain's activity, to the electrodes on the head surface. And the resistive skull is a barrier to that propagation, or what we call volume conduction. So it turns out to be essential that we know what each of the tissues of the head are, and we can accurately estimate their conductivity. This is a complex problem we've struggled with for years, but we have a good general solution in Sorcerer now. The other aspect is good visualization. It's very rich data that we get from the brain, and it's dynamic and complex. So good visualization tools are essential to make sense of the information we get. So Sorcerer has been designed with some very good graphics features from our expert software engineers for being able to see what the data looks like. So we generate the source model from the gray matter, and we can look at that as voxels, and I'll show you we can also look at it as the cortical surface. And this will become a key to going back and forth between the data that's recorded, and here I'm showing a butterfly or waveform view of the data from each of the channels, and the sources, which are shown here in the voxel source model. And if we know the orientation of the cortical surface, that's a big issue. And I'll give you an example in a minute of how we interpret that orientation and its generation. But that becomes key. And we have introduced a new feature within Sorcerer 1.0 that's actually now available, where we use the average orientation of the cortical surface from an atlas, actually the Montreal Atlas of the human brain. So we know the typical orientation of every gyrus and sulcus of the human brain. Now, for the most accurate results, we have to have what we call an individual head model. And that's where we extract the individual's MRI and cortical surface and use that as the basis for the modeling. But as I'll show you today, having that oriented cortical surface from the Montreal Atlas is a very useful tool to allow the inference of what's measured at the electrodes to be translated back to what's going on in the brain. And then finally, we have a flat map. And this is very handy to see the whole brain at once. Otherwise, you have to always be rotating and looking around. And sometimes you miss what's on the opposite side of the head if you can't see it. So we've really put an emphasis on flat mapping so you can see the entire surface of the cortex. But of course, like any mapping, you have to be able to read the map. And so it takes some training to know where the areas of the cortex are on the flat map. So all of that's available now in Sorcerer, and we're trying to develop the best training materials to allow people to get access to that in a straightforward and direct way. I'd like to talk a little bit about both Sorcerer 1.0, but also 2.0, some of the features that we have not integrated yet and we're exploring. And part of my talk this week is to prepare for what I think is a very exciting science talk next week with Mariano Fernandez Carraza and some new analyses he's doing with the application synchronizer, where instead of localizing the brain's spontaneous electrical activity, we are injecting current into the head to influence the brain's activity with electrical neuromodulation or transcranial electrical stimulation. So I'm going to really, even though I'm going to emphasize the orientation of cortical sources and how we localize them in today's talk, I really want to set up for some of the advances in high resolution interferometry using temporal interference models to have powerful new ways of focal stimulation of brain areas that Mariano will talk about next week. But the key really for getting the orientations of an individual's cortex, we began with a number of years ago at the University of Oregon at the Neuroinformatics Center. And I'll just point to some of this because it formed an important basis for the work and source localization we did at EGI, and then the work we did starting fresh at Bell. And I want to emphasize the work of Kai Lee, a University of Oregon PhD student, who helped us develop some of the fundamental techniques for MRI segmentation and cortical surface extraction. And this allows us not only to build high resolution atlas models that we can use for people in general, but also the individual head model construction, where we can build the entire head model for a single individual using the tools that Kai originally developed and now has re-implemented in what we call EMAD, the electromagnetic anatomy delineator. Maybe not the best marketing term, but that's what we made up. And this model, or this graphic here from the University of Oregon, shows our goal to bring a number of constraints to the electrical source modeling problem. Because again, this is an ill-posed mathematical problem that only has a good solution if you impose a number of constraints. So we need to know the tissue conductivities. We need to know the exact position of the electrodes and the exact position of the brain tissues, but we also need to know the orientation for reasons that I think I'm going to explain next. I do want to emphasize that we need dense array sampling. That using just a few electrodes doesn't really allow good source localization. So getting the full surface topography before we even ask the question of where things are generated in the brain is a key issue. And we only do that by adding enough electrodes. So part of our science work over the years has been looking at the effect of different electrode samplings. And the conclusion of this work is pretty simple, that more is better. That we can do a fairly reasonable sampling of electrodes with 130 channels, but it gets much better with our high resolution 280 channel And so having sufficient data to characterize the head electrical fields at the head surface becomes a key goal. Why does orientation matter? It matters because it determines the general direction of the scalp fields from each brain part, each area of the brain. So as it is active, the layers of the cortex include neurons that are aligned in such a way they make columns. And when the whole group of neurons in the column is working synchronously together, it generates a far field. And that means electrical current that's big enough and synchronous enough to be measured at a distance. And when it does this, the far fields are generally perpendicular to the cortical surface. And that's what I've illustrated here on the left with a model of what we would call a radial dipole. It's radial with respect to the head surface. And you can see here, if you look at the arrow right at the center in the cortical surface, it's pointing down. So by convention, we'll make that positive pointing down. So this is a head surface negative field at the outside, but of course, below the cortical surface, it's positive. And that's maybe points to the most common mistake of interpreting brain electrical fields is to think that they're monopolar. So we might describe a positivity like the P300. And naively, we might think that that's a positive field only. But if we understand the generation of electrical fields from the brain, the P300 is also an N300 if you measure it at the appropriate places with reference independent voltage characterization. Now that just goes at the head surface. So every head surface electrical field is dipolar. For every negative field, there's a matching positive field, just by the nature of the generators. But the orientation of the generator, of the part of the brain that's active, is a key factor. So for this radial field I have on the left here, you can see the surface negative voltage will make a big negativity at the scalp where we measure it with an electrode. But you can have an electrode right over that and compare it to the right-hand side, and you will see zero potential at the location of the generator if it's tangential. So here it's oriented not vertically as on the left, but on the right it's oriented horizontally or tangential to the head surface. And right at the site of the active brain, it's zero potential because the positive and negative cross over at the dipole. So this is a principle of EEG generation that the first physicians and scientists to study the EEG intensively in the middle of the last century understood. And they would move electrodes. They only had one channel of electrical recording, but they would move the electrodes around the head to find what they call the inversion point, where the positive and negative fields crossed. That was the source. It's not where the big positivity is or the big negativity, as many psychologists tend to still interpret the EEG. It's actually at the source inversion. Now here in this example, I've also showed the magnetic fields as the big circles going perpendicularly to the dipole that generates the electrical field. So the MEG, or magnetoencephalogram, has different interpretive principles just because the nature of magnetism compared to electricity. But with that, if you ignore the field physics, really the principles are the same for MEG and EEG, and they're roughly equivalent in their precision of measurement. If you have enough electrodes, a high resolution head model, good conductivity characterization, etc. So knowing the cortical surface and knowing the orientation is really key. And it allows us to compare the inverse problem by knowing the forward problem. So the inverse problem is what we start with in measurement. We have a lot of electrodes around the head, and those electrodes need to be high precision. We need to have the amplification, very low noise. We need to manage artifacts, non-cephalic sources. There are a lot of challenges with good EEG measurement. But once we have the signals, we want to know where they come from in the brain. And the best way is to start with a very accurate forward problem, which means a physical model of how activity in the brain will generate the activity at the head surface. And a big ticket there is that knowing the cortex and its orientation, so we have good source models to begin with, and then also to understand how volume conduction is affected by the differential geometries of the head. The skull is the big problem, but it turns out that every tissue, including the cerebral spinal fluid, changes how that voltage field propagates from the brain to the head, and we have to get all of those right to have good accuracy. So part of the goal in developing Sorcerer is to have excellent characterization of the conductivity of the tissue. And in some of our science talks, we'll be reviewing electrical impedance tomography, ways of injecting current into the head and measuring what comes out as a way of really testing the conductivity of the model. And that allows us to understand how features like the scalp and skull and the cerebral spinal fluid affect the volume conduction, the movement of the electrical field through the head tissue. The trick here, and perhaps the most difficult of all of our work, is to have a good characterization of the cortical surface. And this is where Dr. Kai Lee's advances in cortical surface extraction and then dipole tessellation have given us really excellent ways of building this. And both for atlases, where we use the generic human atlas, but that has fairly regular gyral sulcal patterns that are characteristic of most people, but particularly for individuals, because individual cortical wrinkles are unique, and we'll want to know where those are. So that's the goal for Sorcerer. We can tessellate the head surface with enough electrodes, and we can tessellate the gray matter and have enough sources that it characterizes the entire brain to begin our work at that point. Let me just step through some of the procedures that, that Kai developed for the cortical surface characterization. Really, the challenge for this is MRI segmentation. So let's say we have a T1 weighted MRI, a standard structural MRI for the individual. What that is, it's a big volume of densities, and we want to find out where is the cortex. Well, your eye can pick it out. You can look at it and see the cortex, but that doesn't help us. We need a physical geometry of the cortex. We need to be able to segment it, to separate it from the other tissues. And that segmentation is a real challenge, and Kai made some pretty significant advances in the computer science of tissue segmentation. And in fact, we patented that with Kai and actually the University of Oregon in the early days. It's called the relative thresholding patent. And it's still a unique technique. There's been a lot more advances in tissue processing and segmentation, but right now, Sorcerer is able to use on this very sophisticated method. And then once you have that cortical volume extracted, the surface tessellation is fairly straightforward. This uses the marching cubes algorithms that allows characterization of a smooth surface from the geometry of the voxels that you saw on one of the last images. Once we have that, we can then register the electrodes at the head surface. And here we use the MRI surface to characterize where the electrodes are on the outside of the head. And we have procedures to look at that to be sure the electrodes are in the right place. That, you know, you can make a mistake if the head web isn't applied correctly or if you haven't digitized it correctly. And so then we know the relation between the measured data and the brain that it's coming from that allows us to make the characterization. But perhaps the most important part is that for every patch of the cortex, and we can do up to 10,000 patches actually within Sorcerer, 9,600, we know the orientation of the net effective orientation of that patch. And that becomes our dipole model that we can characterize. And that's really the search, is how does that fit? But I want to emphasize again the importance of the skull. Many of the approaches to source localization will not have an accurate skull model. So a boundary element model where we assume the skull is a closed surface is a kind of a poor model because there are holes in the skull. For example, the optic canals that transmit a lot of electricity because the low conductivity of the tissue compared to the skull. The other big hole in the skull is the foramen magnum down at the base of the spinal cord. That changes how the lower electrodes of the head web are affected. And so having an accurate skull model becomes an essential challenge, and we obsess over this for each of our atlases and in the individual head model. It's easy to get a T1 MRI on a person, but not so easy to get a CT because the ionizing radiation. So what we do is we have a kind of a inventory of CTs that we can warp or fit to the individual's MRI. And that becomes a key part of building accurate atlases for Sorcerer, but also doing the individual head modeling, which is going to be one of the key features of Sorcerer 2.0. And then those of you who've looked at Sorcerer understand really how beautiful the graphics are, thanks in large part to Damien Persico, who's helped to implement really state-of-the-art computer graphics visualization to allow a quick insight into what it looks like to see electrical fields in the head tissue. And that's really been an important challenge for us to implement effectively. I want to emphasize another feature that we'll be bringing into Sorcerer 2.0 or maybe 3.0, depending upon how fast Fawn and Xenios move with their current NIH grant project. And that is integrating intracranial electrodes. Now, some researchers now are increasingly working with epileptic patients with intracranial electrodes, and some very exciting science papers that we will be bringing to this seminar series from human intracranial recordings. But for most of our customers, it will really be the clinical setting where the intracranial electrodes are placed for the localization of epileptic seizures. But in some cases, we have been able to record the dense array EEG simultaneous with intracranial electrodes during epileptic events. This is work done with Madoka Yamazaki at Seirei Hospital in Japan. So once the wound has healed from the exit of the electrodes and the scalp craniotomy, then we can put the head web on the head and record simultaneously. This gives us another way of not really a theoretical validation, but a simple empirical validation. And we did this work a number of years ago with the first source localization package we developed, GeoSource 2.0, a fairly primitive, but actually remarkably functional software for source localization. And what we were able to see were some, first of all, that the source modeling was accurate. we could predict what the intracranial electrodes would see from the head surface. And interestingly, we could only predict it because we had an accurate computational mathematical model. Because if you look at the head surface array shown by the big square and the picture of their EEG recordings at the head surface, you can see that what was a big spike inside the brain, and that's shown over in the left-hand column of the colored purple, black, blue lines, is a big spike down in the medial temporal lobe. And what you see at the head surface is a little tiny spike. Now that has led some EEGers to think that the EEG cannot record deep sources. Well, they are attenuated when you're far away from them at the head surface. But the key point here is that there is sufficient information at the head surface with enough electrodes to accurately predict what will be seen by the intracranial electrodes that are placed right next to the source. The only requirement is you have to have all those electrodes have high quality data, and they all have to be included in the mathematical model that configures the geometry. Basically, it's kind of a geometric problem. Where is that dipole generating the field in this head tissue? So with the support of this new SBIR that FON and Xenios are developing right now, we will be able to have the Bell System 1 ready for clinical use for non-invasive localization of epilepsy, but also combined with the intracranial recordings. And we think this will be a key advance for medical use for localizing seizure onset. But actually, I'm pretty excited about it as a research tool to be able to integrate those features together. The other approach that we take that's very important is using perhaps a more crude validation. But this is what we'll be doing for Sorcerer 1.0, but also Sorcerer 2.0 with our individual head model. In fact, this validation I'm going to show actually applies to Sorcerer 1.0. And let me just step through the procedure here of how this validation is going. The first publication has appeared up in the upper right there already in Clinical Neurophysiology. It has good detail on this procedure. The basic logic is if you know that a region of epileptic brain tissue has been cut out, resected, and the patient was seizure free, you have a pretty good sense that that region of the brain was the generation of the seizure onset. So by working backward, taking the data of the spike or seizure generation before the surgery, you can infer, did you localize it in the correct place? So we have a fairly large series of patients now, mostly developed from Huashan Hospital in China, that we're able to use this technique with. And I'm showing the Sorcerer multiple sparse priors, or MSP result. That's the primary one we rely on in Sorcerer. But I'll also show the Loretta, the low resolution electrical tomographic analysis, as a comparison, and the CMEM, I forget exactly what the C stands for that, but it's the minimum entropy of the mean, another Bayesian source solution that Christoph Grobe has developed that we found to be quite accurate as a comparison. So we don't provide CMEM in Sorcerer, we do provide Loretta just as a comparison. But in our validation studies, we want to be able to compare multiple methods. And what you see for this individual is that the multiple sparse prior gives us a very focal result over in that left anterior temporal lobe. And that was where the resection was successful. And it's actually more focal than you would be able to interpret from the resection. Loretta is a reliable and fairly robust technique. And what we find is that it's kind of smeared. It's not very focal, although we do like to have it because we spent a lot of time working with it and understand it. The CMEM and other maximum entropy on the mean techniques are quite accurate as well, but actually in our hands, not as good as the multiple sparse priors solution. So we have a number of patients that we work with in order to do this localization, building the individual head model that we use for Sorcerer 2.0. I guess that's actually the reason why this technique is important, because we are using individual head models in constructing this. So this will be 2.0. So here, instead of using triples, the XYZ component for all of the voxels, we picked the dominant orientation from the Montreal Human Head Atlas, average of a couple hundred people, 157, I think. And we use that as our constraint. And it turns out to be remarkably accurate. So this is work that Kyle Morgan is doing, helping us with our FDA submission for validating Sorcerer in the oriented atlas model for clinical use. And he's going to have a poster at the AES, American Epilepsy Society meeting in December with these results. So if you go back and you compare like the Sorcerer MSP or the other models, the Atlas model gives us a pretty good approximation, a very focal result that we think is accurate as the source of the seizure onset. Here's another patient. So here's individual head model, and with the various solutions. You see typically what we see is that the multiple sparse prior method is more focal and indeed more accurate when we do our own modeling. For example, using a forward generation of a single dipole, we can reconstruct that the most accurately with the multiple sparse prior Bayesian method in Sorcerer. The other techniques are more smeared. They might have the correct central tendency, sometimes not quite, but they're invariably more smeared or less precise and less focal. And on the left-hand side, you see for this individual, the area that was resected and led to seizure freedom is fairly focal itself. And here we're able to reconstruct that. Here's the Atlas model, the individual Atlas model for that same result. So I'll flip back. You can see where the resection zone, where the MSP from non-invasive EEG was. And then here is the reconstruction with the Atlas model. Very close, even using the head Atlas. So I'm actually personally surprised by that. Here's an example that Damien generated within Sorcerer itself, showing that dipole that we localized with the inverse, and now we do a forward projection. Here we made it surface positive, so it made a positive field around the bottom of the head. But this is the forward modeling, where if we take a given spot of the brain, we can see what field it would generate on the head surface. So one of the next things that we're going to introduce, and we're still doing the R&D for this now, but Mariano is leading us in advanced optimized TES, where we work backward from the spot we want to generate. So it's not unlike the forward modeling here. We have a spot here that we want, that in this case, we took dipole 588, generated the forward field out, and we can see the head surface. Well, the question for transcranial electrical stimulation modeling is, if we start knowing that we want to zap that spot, that we want to apply a certain electrical parameter, maybe an oscillatory field at that spot, what pattern of electrodes, and let's assume we have 280 electrodes to work with, what pattern would be able to do that? And that'll be the focus of Mariano's talk next week. And an exciting element of this is that he's been able to, based upon some of the work out of Lucas Perra's laboratory in New York, he's been able to model how to optimize not just a source and sink electrical stimulation, but a temporal interference pattern where we use multiple high frequency signals and have them match up at a certain zone in the brain where they interfere and create a lower frequency from that. It's like interferometry that's used in optics and astronomy, applied to brain localization and brain patterning. So we'll try to give some of the principles of that as Mario introduces his talk next week. But I can point to one example where we've already used synchronizer and the core tools for it. And this is in our work on sleep. So in the publications we have an understanding the slow oscillations of sleep, which is a major focus for our laboratory, and illustrated in the publications by Morgan et al. And Hathaway et al. We've used Sorcerer with that forward modeling that I illustrated to estimate how are slow oscillations generated in the brain. And in fact, we find them generated by deep limbic structures and not by traveling waves across the neocortex. And by using Sorcerer in the forward sense, we can show that if there were traveling waves, this is what they would look like, those top three heads on the left. And indeed, the sources we see in the recorded from the person while they're sleeping are not like that. They're clearly not traveling waves, they're deep limbic waves. Well, with that insight from source localization, our question is, can we manipulate those brain fields? We want to make people have more deep sleep. So how can we put electricity into the head with TES in order to synchronize and to enhance those big slow oscillations coming out of the limbic regions? And that's where we put synchronizer to work. So on the right-hand side, we have a fairly limited number of electrodes that we want to use from our headband system. And we want to know, though, how are they putting current into the head? What is the effect on brain tissue? So on the left, we modeled one of the results that came from Lisa Marshall's laboratory, where she used a milliamp of current and had successful enhancement of deep sleep. So when we replicated it, we used our advanced source modeling and our knowledge that the sources are not in the frontal lobe, but they're really in deep limbic areas. And we also were able to model it, but with half the current. We used half a milliamp, 500 microamps, and indeed it was successful. We got people to extend their deep sleep with this synchronization. So the point is, if you can have your mathematical model fit up with the actuality of the brain tissue, you can have a lot of insight into what's going on in the dynamics. And I'm pretty excited by the next step of this research. And in fact, that's been my goal today, is to kind of set up the background so everybody understands why what you're going to see next week is so exciting. Because Mariano has used these new modeling techniques to integrate the interferometry, or the temporal interference, with our high resolution head modeling to achieve some very focal and a very exciting targeting of brain structures with the dense array TES system, which is still in development. So let me just kind of close with an overview. We need a lot of pieces to do effective research or clinical work with the electricity of the brain. Either it's spontaneous ones or the ones that we impose. And that's our goal, is to put these together. So I'll stop there and be glad to have questions and comments.
Nice presentation. It's a great orientation to Mariano's talk.
Yeah, that's the goal. There'll be a couple of other principles we have to integrate. The basic idea of temporal interference will be important, but what we find with his initial results is that having that orientation, kind of like Fawn emphasized, allows us to target the cortex. And just as the fields are generated perpendicular to the surface, the electrical stimulation or modulation of the brain depends on having the fields that we apply be most effective when they're perpendicular. So the same principle does lead to that oriented atlas as being a key step for good functionality. So it's going to be a priority, and I think, Kyle, we need you to keep working with that and give you the best validation data as possible.
Don, this may be a.
Go ahead.
Yeah, so I heard you talk a little bit in the past about addressing brain shifts, particularly for intracranial mapping.
Yes.
And so I was wondering what are our thoughts on that direction for the future releases?
Yeah, that's a very important point. So the one thing we can say is that the brain shift is important for craniotomies. So that case that I showed was a craniotomy. A big piece of skull flap was taken out. And that's when the brain collapses and there's a big brain shift. For the depth electrodes, where there's just a burr hole and the electrode is poked into the brain, it's less important. But we want to be able to cover both. And Fawn, if I'm correct, then the goal of the Sorcerer intracranial project is to be able to correct for brain shift.
Yeah, you have to do that because once you place particularly for grids, not so much for the stereo EEG. But once you place remove a big flap of bone and then you place the grid in, that's where when brain shift occurs, and then you take the CT to show where the electrodes are. Now you have an image of the brain that's shifted from the original MRI. And so how do you then adjust for that to register back to the non-brain shifted? This is where Xenios's work with his team has been really critical. They have a method for correcting that brain shift so that you can now, once you localize the intracranial electrodes, it accounts for that shift so that you can then register back to the unshifted brain. So that is part of their secret recipe. Not so secret, it's published, but yeah, that's
Good. Yeah, no, that's key because we do the localization prior to surgery.
exactly.
We do it totally non-invasively.
Right.
But then the intracranial recordings are of course done after that surgery. So we have to match them up.
I have a question about the individual oriented dipoles in relation with the TACS. I understand for TDCS, because you have this dipole field, you have a positive and negative, and the TDCS really depending on the positive or negative, you have the suppress or excite different effects, and in that term. And because you explained the pyramidal cells alignment, that the oriented dipole is really important in guiding for the TDCS. But I have a hard time to understand the TACS in relation with the oriented dipoles.
Right. Yeah, that is kind of tricky because in TDCS, you know, we automatically consider the orientation because we have surface positive anodal or surface negative for cathodal. So we already think about the polarity of the dipole and the orientation to the cortex. But actually, it's no different for TACS. It's that same dipole you're working with. It's just that it oscillates. It goes up and down. Now, the oscillations are kind of the whole trick of the brain, the way that it couples networks and the way that things link up. And there's some really exciting new work coming out of the Hallgren lab at UCSD on human intracranial recordings with local oscillations on the cortex at the gamma frequency. So we'll be talking about this in future science talks, how the oscillations are really capturing the population behavior of large areas of the neocortex. But it's the same physics. It's just in one case, you think about it in a static way with TDCS, and the other way you think about it as oscillating with TACS.
That's right. That's right. The key is that whether it's AC or DC is that, you know, if you have current that runs perpendicular to it, you're only hitting like a small segment of the neuron. And that small segment, you know, won't change the polarity or the membrane, cell membrane potential in such a way that it actually influences the way it works. That's why you need the full length of the neuron, whether it's AC or DC, like Don said. In DC, why they place an emphasis on it, of course, is why is cathodal inhibitory and why is anodal excitatory? It's because you only have one direction of the membrane fluctuation. In AC, in a certain phase, it'll be, you know, cathodal, similar to a cathodal as an example, and then in a different phase, it'll be like a anodal, and you're just fluctuating between those two states. But to achieve that, again, you have to have a net membrane difference at one pole or the other of the neuron, and you can't get that if it's perpendicular. Does that make sense, Wei?
Yeah. I think I kind of start capturing.
And Wei, maybe you can think about, I can't remember the name of the lab, but an interesting set of papers where they were looking at in patients with Parkinson's, a certain oscillation in the hand in the periphery. They could measure that frequency and inject a similar frequency into premotor motor cortex and then shift the phase. And they could make that
Tumor,
make the tremor worse or better, cancel it out completely in some cases. And there was some controversy around it to start, but it's been replicated. It's complicated, but I think something else, and I would make a prediction outside of the kind of classical, these pyramidal neurons, the summed voltage that's grouped together. We've got that, but I think something else that might come from this is when we start adding in different physiology, cognitive experiments, and we see effects at certain frequencies that are resonant with some of the cortical regional differences, like the layer 2-3 GABAergic interneurons that oscillate at different frequencies from some of the other areas. And you can imagine targeting that differentially or maybe teasing apart certain physiological effects. I think some people are going to design some really cool experiments with these tools.
Yeah, I think that's why the human intracranial recording is so interesting, that because the local field potentials recorded right in the cortex are so instructive, but we're not so far away with our source localization with a dense array of electrodes. So being able to go back and forth between the intracranial and the head surface, I think is going to open up a whole new era of non-invasive electrical neuroimaging at the head surface. All right, maybe we should wrap at this point. Thanks for your questions.
Thanks for the talk.